Welcome. In this video, there is no new material. We will just review what we have done before. Because remember, I told you, I keep saying this almost every video. Yeah? I told you groundwater is easy to study because you only have one equation. That's Darcy law. But this equation, even though you think it's simple and you understand it, it has a lot of subtleties to it. So now I will challenge you in this video and I will show you that maybe you think it's easy and you understand it, but maybe not. Maybe there are some subtleties there that you didn't get. And that's why with this tricky example and this tricky problem that I will keep giving you by challenging you, that's how you will have developed this deeper understanding of what we are studying. So basically what we will do now and what we will be doing next, I will be just challenging your understanding until I get these like what the objective of the first four modules is. What the objective of the first four module is: two things, is conceptual understanding and fundamental skills. I want you, before we go to applications, like before we go to field work, modeling, blah blah blah, before we go to this application, as an engineer, uh, you need to have a good and solid uh, background, conceptual background upon which you build our knowledge. And this conceptual background, this is not just some, how do you say this? This is not just something to show that, oh, I'm clever, or I understand more, or something like this. Is not like a show off or anything like that, but it is essential. Like if you are at a field, if you are having a groundwater project, if you lack this fundamental understanding, that might affect the work you're doing, as I will be showing you. So this conceptual skills and fundamental conceptual understanding and fundamental skills, they are essential, yeah, before we move to application. Yeah. Okay, so let me challenge you. So basically, we will apply Darcy law, yeah, to do back of the envelope calculation, some simple calculation. And this simple calculation will show you, or maybe some of you, or many of you, or most of you, that your understanding of Darcy law was not as accurate as you thought it was. Yeah, but some of them will be simple and straightforward. Some of them will be more challenging. Not just understanding of Darcy law, that's like your understanding of fluid mechanics also and other subject, yeah, because you develop this subtle understanding uh, by like looking at this tricky question. So I'll be doing this here, and I will be doing this a lot in the next module. You have one whole lesson about these things, yeah. Okay, this is your social media activity, or Instagram or Twitter or Facebook or whatever activity. Okay, let's look at this example here. So this is the Kharga oasis in Egypt. Uh, uh, like you see this images here, because people have lived there for more than what, 2,500 years. Yeah. How old uh, that's almost like like how, for how long have been human being on earth? Like, can anybody know for how long we've been on earth? I mean, we don't know exactly, but based on the evidence we have, about like 400,000 years. And this place, we have evidence that people have been there for at least like last 2,500,000 years. This receive 1 millimeter, 1 millimeter rainfall per year. This is not per day. This is not per hour. Like here in this is like per year. Yeah. So this is the most arid region on Earth. So this is here. This is Saharan desert. This is one of the. This is probably the most arid region in the world, in the Saharan desert. This is where you have like this quicksand, like where you go, the sand will eat you. This is probably has places that, yeah, even the most like daring explorer has not, like of our modern time, has not been there. But how do people live there? Obviously, the people live there because there were some oases there, and there are still. Not only there were, but there are some still, like some oases there. And oasis, that's like a phenomenal thing. So you walk in the desert, it's an area that's almost dead. There's nothing alive, and then you find this green place inside the desert, and that's like an oasis. And I mean, but how could this green living environment be there if you are only getting 1 millimeter rainfall per year? Well, thanks to groundwater, thanks to unconfined aquifer, and thanks to artesian wells and high groundwater pressure. So that's historically people have lived there because there was this artesian well where you just can easily water can just gush out like even without you doing anything, water just the groundwater will just gush out, will vent out, yeah. And or you just make small puncture and then the water will get out, yeah. So that is basically why it was there. But now, like this region, like in Egypt, so this is Egypt, this is the Nile Delta. So Egypt population is about 120 million. Most of them would be like living here in the Delta and across the Nile. A little bit, some population would be living in Sinai, but this is mainly like tourism and like a local population. And all Egypt is like desert, yeah. So this is like the desert. This is the Saharan desert, and you find some oases there. So like you will find like within this desert, you will find some oases there. One of them is this desert, and this desert gets its water from what's called like the Nubian sandstone aquifer. So like you see here, this desert gets some its water from the Nubian sandstone aquifer, and this Nubian sandstone aquifer, I'm just like roughly see, it is shared by like three countries. It's shared by like Chad, four countries, sorry. It's shared by like Chad, Egypt, uh, Libya, and Sudan. Yeah, like so this four country like shares this aquifer. It is the largest, like it's called the Nubian sandstone aquifer, and it is the largest non-renewable aquifer on Earth. And again, when I say non-renewable, I mean non-renewable on a human time scale. Any aquifer would be renewable on a geological time scale, but human time scale, like hundreds of years, non-renewable. On a scale of millions of years, yes, it could be renewable. It could be renewed again. Okay. So let's do some studies here. So like, I'm like, let me make another advertisement. Yeah. I made like in the previous video, I make an advertisement about Kiri Gold. Like here, I'll make another advertisement about if you ever visited Egypt, you will find you can find many companies that sell mineral waters, like bottled waters. And usually, this is groundwater, like mineral water. So that's all the most of the companies in Egypt who sell this like bottled waters would be mineral water, like groundwater. And one of these companies, they will get their water from one of these oases, which is like here, the Siwa oasis. They will get it from here, yeah, which taps through the Nubian sandstone aquifer. So this water you'll be drinking, it has a distinct taste. Some people in Egypt don't like it because it has this metallic taste because it's full of minerals. So it has like this metallic taste because different water will taste differently. Waters that are high in, for example, nitrogen and phosphorus will taste different than waters that are high in minerals will taste different than waters that has algae plumes, like not harmful algae plume, but useful algae, not blooms, useful algae. So each water differs. So this water will have a little bit of a metallic taste to it, which people don't like. But this water is probably one of the most pristine water you will get. I mean, at least as far as I know, because there are a lot of agriculture, so it might have been contaminated now by some runoff from agriculture, like leaching from agriculture. But it's still like one of the most pristine water I will get. When I went to Hawaii, they were telling me the water you will be drinking here is like 100,000 years old. So it's a pristine water that's 100,000 years old. Well, I told them, oh, this is young. I told them, compared to the waters that my favorite water that I like to drain in Egypt is young because the waters that I like to drain in Egypt is about 1 million year old. And how did I know this? Can we do this calculation? Can we calculate like how old this water is? So maybe, yeah. So let's see how old. Like if you ever went to Egypt and you're drinking this seawall water, can it be like 100 million year old? How can you? Just a back of an envelope calculation. So this is a very rough calculation. Remember, there's hydraulic conductivity value. They are heterogeneous. So each of these parts, like each of this here, 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 each one will have its own hydraulic conductivity. But if we just get an average hydraulic conductivity for this whole area, then we can do some calculation. Yeah. So here I just like let's read this problem. Like Kharga oasis in Egypt, water come from Nubian sandstone and flow over 800 kilometer from the intake base. That's the recharge area. So water gets recharged here. Yeah. So water gets recharged here. So that's where the water will get into this aquifer, this Nubian sandstone aquifer. So this is the intake bed, and then water will travel all the way here to Kharga Oasis. And what do we have here? So that would be 800 kilometer. Yeah. So that's like 800 kilometer. Okay. Assume the same hydraulic conductivity and effective porosity. So remember, like the hydraulic, so assume that like all these areas, so I measured hydraulic conductivity here, 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 here at different bar, and then I found like an average value for the hydraulic conductivity. Remember, this is just a back of an envelope calculation. So I find the hydraulic conductivity to be 1.5 meter cube per day. Yeah. So assume that this is the hydraulic conductivity, 1.5 meter cube per day. And then the effective porosity, remember you need effective porosity to calculate, to change Q to V. Yeah. And the effective porosity is this much. Now, how long does it take for groundwater to move this 800 kilometer? So what I want you to do, I just want you, like, before you look at the answer, yeah, before you look at the answer, I just want you to try to solve it by yourself, and then we will solve it together. So pause the video. All you need is Darcy law. Yeah. So all you need here is Darcy law. So that's easy, like negative uh, k, like q is equal to negative k I. So here, what you need to know is like, so the distance traveled, and you need to know the, like here, let me write instead of I. So let me, this is delta H over delta X. Okay. So delta X is given. Yeah. So delta X is given. That is like 800 kilometer. Delta H, the difference in head, you can calculate it. So I'm giving you the contour of the head. So basically, like if you look at this contour here, like if you want to calculate like delta H, so let's see how you can do this. So we do here as the intake. So that's basically like you get here maybe 500. That's the head here is about 500, and at the Kharga oasis, the head here would be around like 100. Yeah. So is this correct? Yeah. Mm, So yeah, I mean it's about right. So if you did this, this is yeah. So that's the Kharga oasis. That's about 100. So delta H would be like uh, that's this contour here. Yeah, that's like 500 minus 100. So that is like 400. And these values are in meter. Yeah. So that would be in meter. Okay. Uh, So that's basically like what you will get, yeah? So like here, like let's just make it I, yeah? You can say like this is I, so I is equal to delta H over delta X. So what is this? So delta H, what is it? Delta H, what's delta H? That's like 400 meter. What's delta X? That's like 800 kilometers. So let's just 8, oops, to the power of 10 to the power 3 meter. Yeah. So meter will go away with the meter. This guy will go away with this guy. Yeah. I will have 2 here. Then I will get something like point zero zero. Yeah. Another 0, fine. Yeah. So that's like 1 over. Yeah. Yeah. So you get something like this. So that's like your I. Yeah. And so your K. So let's see here. So and oh, remember here that should be negative. Let me just do this. That should be negative because remember this is like your H2 here, and this is like your H1 here. So that's like H2 is like 100 minus H1 is like 500. So you get minus 400. Yeah. So your I is just like negative. And so here you will multiply this by this one. And if you did this, you multiply like this is your K, this is your I. So if you multiply this, I got a Q of 0.0000, yeah, 75 meter per day. That's like the Q that I have, yeah. And do you remember like V? Remember V? How to get V? This is like Q over NE. So if I divided this by Ne, like the effective porosity that I have, then I will get, so if I divided Q by Ne, then I got like 0.0002 meter cube per day. Okay, so now, so remember like velocity is like distance over, oops, velocity is distance over time, yeah. Now I want to find time, so time that would be distance over velocity, yeah. So what is the distance? So the distance is already given, like 800 10 to the power 3 meter. And the velocity, this is the velocity 0.002 meter per day. So if you did this calculation, I got, this is the times that I got. Like, so if I did this calculation, the time that I got is 3.6 10 to the power 8 days. 3.6. So this is approximately equal 1 million year. So that's about like, so the water that you drink, like from the intake, so the water will fall here somewhere in Chad. So this is like somewhere in the Chad, for example, or whatever this intake is, and it will infiltrate into the subsurface. It will recharge the aquifer. It will keep traveling for 1 million years until you get it here in Egypt in the Kharga Oasis. And that's how people live there for, we could trace human bags there for more than 25,000 years. Okay, because they got this water, they are drinking this water, which has been there for like 1 million years. Okay, and now you can just do this back of the envelope calculation. Like if somebody challenged you, like how to do this, just go on the internet, grab any research paper about the Nubian aquifer system. You'll find some hydraulic conductivity values. This is basically what I did here. I just went, I did like a Google search or whatever, or a search on Web of Science, and I just found papers that are related to this Nubian aquifer system. I find like an average K value for all this. Like I just calculated this average K value. I assume that porosity is 1 over 3. This is just an assumption, a quick assumption that I get. Then you get a map like this. You can get it also from any image or research papers that you will find online. And then you just do your calculation. Yeah. So, so you can get this from, yeah. And then you do your calculation. Okay, let's do one more. We are still good in time. Yeah. Let's do one more. Again, I'm challenging your understanding. Yeah. Let's let's do one more simple application like of Darcy law, yeah. And you need to understand like uh, so now the average hydraulic head in aquifer 1 and 2 is like 11 and 12 meter respectively. So I have aquifer 1 here, and then I have aquifer 2 here, and the head here, like so the head, and assuming it's vertically constant. So head usually it does not change in space, like vertically it will not change. So like the head here is 11, the head here would be 11, the head here would be 11, unless, because we generally assume that groundwater flow would be vertical, horizontal, yeah, unless you are like near to a river or near to lake or whatever, then you will start have like groundwater will not flow horizontally. It will start to flow maybe like this or whatever. And then in that case, in that case, you will like the head will not be constant vertically. It will be like, for example, like if the water goes from up to down, then the head here should be higher than the head here. Yeah. But for most cases, we assume horizontal groundwater flow. So head here would be like 11, and head here would be like 12. Yeah. No, sorry, 11, not 12. Yeah, 11. And head here would be 11. Now in aquifer 2, the head also is 12. So the head here would be 12, the head here would be 12. Yeah. Now, the hydraulic conductivity of this aquitard, so K here is 0.01 meter per day. If I want to confuse you more, I will just tell you the hydraulic conductivity without saying aquitard or anything. But I don't want to confuse you more. I think that's challenging enough. What is the flow rate per unit area between the aquifer? Per unit area means that like if I just like have like 1 meter here, 1 meter in the x direction and 1 meter in the y direction. So I have this column here, and like this column, what would be and this, like the distance from aquifer 1 and aquifer 2 is 10 meters. So in this column, like just 1 meter by 1 meter, how much water I'm expecting to see, like what is Q? So basically A in that case, so A, that's like your length time width, so that's like L time W, L time W, so that is like 1 meter cube. So here this part is easy. So this part is easy. So this part is like 1 meter cube. Okay. Now we need to understand something. So I told you, like you need to understand what this problem is exactly asking you. So this problem is exactly is what is this problem is telling you that the head here is 10, the head here is 12. Yeah. Okay. So let me delete all this. Yeah. The head here is 10 and the head here is 12. Remember, I told you flow direction, like groundwater flow direction is always like this. Yeah. So here flow direction would be like this, here like this. That's in the aquifer. But I told you the aquitars, this is a confining layer. So there is usually no flow between like aquifer 1 and aquifer 2. But there is like this is not accurate because there I told you there is like little flow. So it's not that there's no flow, there is the little flow. So in addition, like your main flow would be in aquifer 1 and aquifer 2, but across this aquifer you will still have some flow. Yeah, you will still have some flow. It would be little compared to what is to this one and this one, but still some flow. So now the question is, remember, flow is usually from high energy to low energy. From high head, like energy, you measure energy by the head, as you learn it in fluid mechanics. Uh, and you measure energy here by the head. So you has the flow is from high energy to low energy. What does this mean? This means that the flow direction, it would be from aquifer 2 to aquifer 1. So the flow in the aquitard, it would be like that small flow, it would be from aquifer 2 to aquifer 1. So that is basically would be my flow direction. So what is delta H here? So delta H, remember, like delta H, that's like H2 minus H1. So what's my H2? My H2 would be like, so that would be like my H1, and that would be my H2. So here, that would be like 11. Yeah, so that would be like H2, that would be 11 minus H1. So that will be negative 1. And delta L, that's the distance of flow. So delta L here, delta L, that would be 10 meter. Delta L, that would be 10 meter. And this is 1 meter. Yeah, so what is I? Like I is delta, let me not, let me just write it delta, not partial. Delta H over delta L. So that would be like negative 1 over 10. Yeah. So that's like negative 1 over 10. So, and that would be like, that's what? That's dimensionless and unitless. So that's we get negative 0.01. Okay, so that's basically, now it's easy. Yeah. So now I have the Q. Yeah, please, please pause the video, try to solve it. Yeah. Okay, so try to solve it in your own and see if you're gonna get the same numbers that I have. Okay, but anyway, welcome back. So here negative K, so I have negative K 0.01 time the area, that's like, so negative K, and let's write the unit. Yeah, it's always good to have that's like this meter per day, time area, that's like 1 meter cube, time I, which is like, this is I here, which is negative 0.1. So if I did this, what will I get? I will get 0.001 meter cube per day. So in 1 meter of this aquifer, like, so over like 1 meter width by 1 meter here, 1 meter length by 1 meter width over a distance of like 10 meter, each day I will get, that's about like 1 liter per day. So you see, like, you don't even like see, and that's why I told you there is almost no flow. You got 1 liter per day. Imagine over like a length of 10 meter and 1 meter by 1 meter by 10 meter over this volume, over a volume of like 10 meter cube, you only get 1 liter per day. That's not enough for like the minimum water you should drink each day is 2 liters. So that's not enough even for one person. And that's why we say that there is almost no flow here, because it's just 1 liter per day. Yeah. Versus here, you will find like tens or hundreds or even thousands of meter cube flow per day in like this direction. Yeah. Okay. So now again, like, now you think you understand like how the groundwater head, like, or hydraulic head. I will later in the lesson, I will challenge you until I make sure you understand like this hydraulic head. You studied these things already in fluid mechanics, like head, the concept of hydraulic head, but now now this is a more advanced course, so you will start to study it more advancedly, and you will start like seeing the subtlety of these things. But here's this example. Try to understand it. Try to see that the flow direction, like, read the problem, and then you see that we are applying the flow direction is from here to here. That's what I'm asking you to do. Like, the head here is 12, the head here is 11. So flow would be from high head to low head, from here to here, from high energy to low energy, because I told you flow is always perpendicular to this one. So flow, so that's like your energy line, like your hydraulic head. Yeah, that's like your head. So this is 11, this is 12, and flow will always be perpendicular to this one. So flow will be perpendicular to here, flow will be perpendicular to here. Similar to what we saw in the previous example. So here, this is my hydraulic head, my head level, and you see flow is perpendicular to here, 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 flow is perpendicular to here. This is head here is 500 meter, head here is 400 meters, 300 meter, head here is the lowest hydraulic head we got, which is 100 meters. So try to develop these concepts. These are things you already studied like in fluid mechanics, but I want you to now see it in real application or see how you apply this in real application. Yeah? Let's do one more. Let me challenge you even more. Yeah. So I will challenge you here even more. How we are doing in time? I think we are doing good. Still have about like 20 minutes for this video to go. Hopefully I'll take less than that. Uh, okay. Let's look here. Yeah. Let's study this problem carefully and we will apply several concepts we've seen before. Application of Darcy law. So here, like you have that. So this is a confined aquifer. So here, this is a confining layer. Yeah, this would be the confining layer here. So you need to understand your problem carefully. And if I measure the hydraulic head here, like at this point, okay, so the previous one was a bird view, this is a cross section. So, yeah. So if I measure the hydraulic head here, like I put a piezometer and I measure like my head here, then it will be like 20 meter. If I put like a piezometer and measure like the hydraulic head here, it would be this value which is unknown. If I put a piezometer here and I measure this value, I will measure the hydraulic head is 50 meters. And remember, this is my water level. This is the hydraulic head. So remember, this is my potentiometric surface. So that's my potentiometric surface, and this is my water level. And that's what we know about confined aquifer so far. Yeah. So that's a confined aquifer. Now, I'm asking you several questions. Like this piezometer here, I'm asking you what is the head? What is this HM? Like what is this HM? So I know the head here at like the beginning of my aquifer at this piezometer. So at this piezometer, I know I measure the head here. At this piezometer, I know the head here. Can we find the head at this piezometer? Can we calculate this? Yeah. Like, or can we calculate the head at this point? So that's like, that's how much, like, that's the first questions that I'm asking you. Okay. The second question that I'm asking you, what is the flow rate in the aquifer per unit width? So that's like the aquifer. So this is the length of the aquifer. So the length of the aquifer is like 2000 meter. And that's the depth of the aquifer, that's depth. But I'm asking you like per unit width. So like just per unit width. So like here's the width, here would be like 1 meter. Yeah. Per unit width. Yeah. So if I look at this area here, yeah, like this area here, so like if I look like I just do look at this area here, which you have here, so that would be like 1 meter, and that would be like 10 meter. Yeah, that's what we have here. And like so, I'm telling you what is the Q in this per unit width. Yeah, in this here over this length. That's the length of the aquifer here that we have. So that's area here. Okay. So that's the second question. And then I'm asking you, what is the average hydraulic conductivity? So what is the average hydraulic? So I have like K1 here is this one and K1 here is this one. So remember, we can calculate the average hydraulic conductivity using this formula, which we learned before, the uh, uh, harmonic average or geometric average. I still didn't check which one is this, harmonic or geometric average. This is the difference between harmonic average and geometric average. And please check it. I still didn't check it, but you can check it and you can check it and let me know in your exit ticket. Like, is this equation for harmonic average or geometric average? Yeah. Not simple arithmetic average. So you have arithmetic average, weighted arithmetic average, and then harmonic average and the geometric average. So see which one, which one is this? Okay, that's your you need to do for your exit ticket. Okay. Okay, so let's look here. So you can use this equation to simply, or you can use this equation, like, because if I know, like, I know delta H, yeah, I know L, I know this length, so this is giving, so this is like 2000 meter. Delta H, this is giving, this would be like H2 minus H1, that's like negative, so that's 15, negative 20, so that's like negative equal negative 5 meter. So I can calculate this one. The area is giving, so that is like 10 meters square. Q, I can calculate Q, so I need to calculate Q. I can, that's one of, so if I know Q, then I can calculate K. Then I can, so if I can calculate Q, which we will see now how to calculate Q, or how to calculate like these things. So I can calculate Q, and then, so if this is known, then I can solve for K. So I can do it this way, or I can do it this way. But we will look at this later. Let's just start by uh, finding this HM as the piezometer, like this HM here as the piezometer. Like, what is the head here at this piezometer, like this HM? How can you do this? Yeah, how can you find this HM? So let's do our Darcy law. Yeah, all we have is our Darcy law. So we have Darcy laws as Q is equal to uh, like negative K, yeah, the area delta H over delta what, L, or delta X, or whatever. Yeah, I'll just call it delta X. Yeah, just uh, that's my X direction here. Yeah. So if that's my X direction, so you need to define, like, that's my X direction here. Okay. So now I'm asking you to find this guy. What do we know? So we can either like, so you, like, use this guy or this guy. So if we looked at this guy, now we have a problem. Like, we K is given. So like, let's write it down and see what problem do we have. Yeah. So I'm just like looking at Q2 now. Like, this is Q2. So I will just, so for Q2. So the problem we have is that we have negative K. So that's negative K is giving like 50. Yeah. The area is giving, so that's like time 10. Uh, and then delta H is giving, what's delta H? So that's like H2 minus H1. So what's H2? That's like HM minus H1, that's minus 20. Over delta X, that's giving like 1000 meter. So that's basically from here to here. Well, I have a problem. What is my problem? I have one equation and two unknown. So Q is unknown and H is unknown. So I need another equation. So what would be another equation? Well, I can do this one. I can do another equation for Q1. So at Q1, yeah, uh, I can do like for Q1 here. So Q1, that would be negative K. K is 100. Yeah. And area, again, like, before you see the answer, try to solve it on your own. Like, all these problem, pause the video, try to solve it on your own before you look at the answer. Okay? So that's like here, and then time like H2. What's my H2? That would be like the 15. So that would be 15 minus HM. That would be like your H1, because this high head to low head, and divided the distance is 1000. Okay. But now I have another problem. Now I have two equations, but in three unknown, Q1, Q2, and HM. So what do I do? Well, that you need to remember what you have learned in fluid mechanics. So what did you learn in fluid mechanics? Do you remember? Continuity equation? Yeah, do you remember you did something like this, the conservation of mass, the continuity equation? So let's see here, like, this is Q, like, this is, like, let's see, this is here, this is a Q naught, like, this is the Q that's entering here. Let's call it Q naught, for example, Q0. Yeah. What is this one? Would this one be equal, like, based on like what if you remember what you did in fluid mechanics, the continuity equation, like this Q1 would be equal to this, like, Q2 here, would be equal to this, like, Q2 here, be equal to this Q1 here, would be equal to this whatever Q here. Because that's by continuity equation. Like in a steady state, yeah, in a steady state, what is coming into your system, like how much the water that will be, that's the definition of, oops, what happened here? I think I did something. Oops. In a steady state, remember, like in a steady state, what's Q in? That's by definition. Q in is equal to Q out. That's like steady state. Like so, in a steady state, like Q2 minus Q1 is equal to 0, which means like Q1 is equal to Q2, which means Q here is the same. So basically, like this Q2, that's my third equation. Q1 is equal to Q2. This from continuity equation from what we learned in fluid mechanics before. And now I have my third equation. So now like basically like you can just say this is equal to Q. So you can say this is Q and this is Q here. You equal these two. So now you just you will equal this and then you will solve for this one. And if you did this, if you solve this, the HM that I got here, that's 16.67 meter. Okay, good. So now here is 20 meter, here is 15 meter, and the head here, like HM, that would be something in between. Otherwise, remember, flow is from high hydraulic head from high energy to low energy. So that's 16.67 meter. Yeah. So that's like high energy to low energy. This is high energy to low energy. And that's why that would be your flow direction. Okay. Now I'm telling you to calculate like Q. Yeah. So now Q is easy. Yeah. Like how to calculate Q. You can just substitute like this HM, like in this equation here or in this equation here. So if you just substituted this here, then you get something in negative. The negative will cancel here with the negative, and then you will get your Q. So if you did this, so the Q here, we solve it for this one. Let me show you the answer. So like if you substituted this, you just like we got HM here, that's 16.67 meter. Yeah. And then Q1 and Q2, you can substitute like this guy like here or wherever you want. Like this one is slightly different because I'm not like using the negative sign here, but it really doesn't matter. If you solve it this, you get like Q is equal to 1.67 meter cube per day. Okay. So try to do it, see if you can get the same number. But the important part here is that you'll not plug like this number and like you just like crunch some number into an equation and get. That's not the objective of these exercises at all, because that's not useful. Yeah. What is useful is that I want you to develop your conceptual understanding. I want you to connect dots. Like, what is hydraulic head? This is the water flow from high energy to low energy. Hydraulic head measures the energy. So if you don't remember this, go back to your fluid mechanics and like revise this. Like flow from high energy to low energy. Here I have like two hydraulic conductivity values. So here I got, because I have two hydraulic conductivity value, I got here, this is 16.7. So I got like this here, and I got like this a little bit more shallow here. This is more steep. This is more shallow. I will show you this later. Like, see the energy loss here, you are losing energy. So this is like 16.7. This is here 16.67. So I'm losing energy here very fast. I'm losing energy here very slow. And I will show you this like more. Okay, now I'm asking you what is the average hydraulic conductivity. So you can easily do this. Yeah, you can, you know Q already. So we calculated Q from the previous example, that was 1.67. We know the area, that I think was 10. Uh, Hello? That was 10. Uh, that was 10. And H2 like you can just get it. So that would be H2 minus H1, that would be 5. And that's this. And then you can calculate the hydraulic average. And if you did this, the value that I got, like if I did this correctly, let me show you the answer here. So that's the value that I got, like 66.7. But you can also do it the other way. You can also do this using this equation. So please pause this video, try to do both way, and make sure that you will get like these answers that you see here. Okay, so that would be a good review also for using the harmonic mean. Okay, or the harmonic mean equation, because that would be like in your homework, and that would be also in your exam. Yeah. So now let's look here. That's like more conceptual understanding, yeah? So Q, like we know that Q is constant. Yeah, K is different because of heterogeneity. So here we have two faces. This could be like a fine sand, for example, and this could be like a medium sand because this has a higher hydraulic conductivity than this one. And you see here now, this is what I want you to see. Like the I here is different than the I here. So I here, like see the I here, like let's say, let's call this I2 and let's call this I2, like your hydraulic gradient. And they see like the hydraulic gradient 2 is larger than the hydraulic gradient 1. This is again conceptual understanding. Why? Why is it this case? Because as water moves from here to here, this is the fine sand. So you, what does fine sand means? Like you have low hydraulic conductivity, you have high friction. So this friction will what? Like part of your energy will be converted to heat energy. So not all the energy would be used for flow. Part of this energy would be because of the low hydraulic conductivity. Part of this energy would be like converted to heat energy, and that's why you have a big, you have this steep gradient like this is 16.67. You have this steep gradient here, versus here you have a gentle gradient because you have like less friction, less heat used to friction. So much of your energy is preserved here. And that's why you have a gentle I here and you have a steeper I here. The area is constant, and that's why, and that's basically what this equation is telling you. It's telling you if if k go up, q is similar. Yeah, so this is the equation. Let's put it in small q even, just to put it in the simplest form. So you have k and you have I. So that is like, this is from a mathematician perspective. Like, let's say you don't understand anything about like hydrology, fluid mechanics, you don't understand anything about groundwater, you're just a mathematician. So a mathematician will tell you, yeah, I mean, if K go up, yeah, the I will go down. And that's exactly what we see here. Like K go up for this equation to hold. Like if the value, if you have a higher hydraulic conductivity, a mathematician doesn't know like what is K, what's I, but he knows math. Yeah, so he knows math. Like if K go up, this will go down. Yeah, if this goes down, this will go up. Yeah, for this equation to hold. So now I want you to whether like use your fluid mechanics and groundwater hydrology expertise or your just math expertise to answer these questions here. So you can either answer them as a mathematician or you know, like based on like as a hydrologist, yeah, groundwater hydrologist and fluid mechanics, yeah, from fluid mechanics. So now here I'm telling you column A and column B. So here you have a fine sand and a coarse sand. And I am telling you K1 is greater than, less than, or equal to K2. So giving these images you have here, yes, is like K1 greater here or here. Which do you think would be the case? So again, if I am a groundwater hydrologist, I will like say, okay, I could just use my knowledge that I have. So I will say, okay, this is a coarse sand, this is a fine sand. So based on my understanding of K value, this should be have like K2. In that case, K2 would be larger than K1. Yeah. So that's from a groundwater hydrology perspective based on my understanding of K. Yeah, so K2 would be larger than K1. Now, from a fluid mechanics perspective, I will say, you know what? I have here a very gentle I. I have here a very steep I. And if I have a gentle I, what does this mean? This means that I don't have much friction, like I don't have much energy loss. There is not much energy loss, and not much energy loss means what? Not much friction. Not much of my energy is lost to heat. What does this mean? This means I have higher hydraulic conductivity. Flow can pass more smoothly. So basically, so in that case, also from fluid mechanics perspective, K2 should be higher than K1. If I'm a mathematician, I will say, I mean, I don't care, you know. I just look at this equation. I don't understand any of these things. I don't understand any of this fluid mechanics people do. I don't understand any of this groundwater hydrology do. But what I can tell you, if if K go up, I will go down. So which one has a, so this has a higher I, so this one will have a lower K. This has a smaller I, so this will have a higher K. So I will just from a mathematic perspective, I'll tell you also K2 is larger than K1. So see from three different perspectives here. Now let's look at this example here. Again, this is both are fine sand, and I'm telling you which is like I'm telling you Q1 is greater than or smaller than Q2. Yeah, so which one is greater? Like is Q1 greater than or less than or equal to Q2? And both are fine sand, and both are this one. So which one would that be? Like so, pause the video, think about it, and get back. Yeah. Uh, okay, so obviously Q1 should be larger than Q2. Why? Because I have higher energy. So if you have higher energy, so like you see here, like so if I have higher energy, this means I can pass more water. I can push more water. I have more energy to higher flow because I have high energy. Like this is higher than here. And this is basically like, how do we know this? Like Q is equal to negative K A I. So K is the same, the area is the same. If this goes higher, this will go higher. This is just from a mathematic perspective. Like if this is the same, this is the same. If I go high, Q will go high. Now, this is my last question for you. Uh, this is both are fine sand. Like this is fine sand, this is fine sand. Q is the same, so like Q, like this is Q here, Q1 is equal to Q2, and I'm telling you which one will be steeper, like which one, like which I will, like hydraulic gradient I, like you will get like I, like let's say this is I1, like I1, and this is I2. So I'm asking you, is I1 equal, larger than, or smaller I2? So think about it and let me know the answer. Hydraulic gradient more steeper, so I'm telling you this is more steeper or less steeper or not. So pause the video, think about it. Again, use the same analogy here, and then let me know. So obviously, QI would be more steeper than I2. Why? Because you have much energy loss because this you have a small area and you are squeezing like here, so that is like, so that's like Q is equal to negative K A I. So Q is the same, yeah. The area is the same, sorry, the K is the same, yeah. The area is the same. So if A go up, if the area go up, the I will decrease, yeah? And that's exactly like, so that would be gentle because the area is have a bigger area here than here, so that would be gentle, yeah? So you get something, oops, you get something that looks like this. So this is steeper, this is gentler. So with this, I will like wrap up this video. So here groundwater flow is controlled by hydraulic gradient and permeability. Now you should know like the steeper this one, the more Q you will have, but this also, so that's like Q is equal to negative Ki. So this is a hydraulic gradient. The steeper this one is, the higher will be the Q, and this is the higher this one is, the higher will be the Q. So which means you get more Q in gravel. Q here would be larger than gravel would be larger than in sand, which would be larger than clay. So that summarizes this thing. Next, this is more like conceptual understanding. Uh, Please, you can read what I have here, so you can read this. This is more like a conceptual understanding for this topic. Next module, in the next two module, we will do this more quantitatively. Still, there will be more conceptual understanding. I will still keep refining your understanding for hydraulic head, hydraulic gradient, all these things that you learn from fluid mechanics and relation to hydraulic conductivity, but it will be more quantitative in the next video. We'll start to look at groundwater flow equation and things like that. So, okay. So that's all like for this video, and I will see you in the next module.